I will try to just now give some conclusions now. I will not go into math and all, try to give conclusions very quickly. So this is the gate and drain are connected together, and therefore this is the, now we have seen that this transistor is acting in saturation, all right. This is acting in saturation, but then can I use it as a current source or not is the question. If I want to use it as a current source, what is the requirement? Again, voltage, even if the voltage, this voltage varies, the current should not vary. Even this voltage varies, current should not vary. So, but in saturation, no, therefore it appears that I can use it as current source, right? Is it true? Appears to be, but all things which are appearing may not be true. So we can see that as VDS is varying here, VGS is also varying, because drain and gate are connected together. Drain and gate are connected together. As VDS varies, VGS also varies. As VGS varies, current is bound to vary. As VGS varies, current is bound to vary. Though it is in saturation, but because VGS is also varying, obviously, see earlier what we said is as VDS is varying, keeping VGS constant, current is constant. Yes. But here I am violating that rule. That the mutual funds risk factor, we have not studied properly. Therefore, what happened? Here VDS is varying, but VGS is also varying. Therefore, current is varying. Therefore, it cannot be used as a current source, right? But anyhow, I can use it as a load, simple load, and I can design some simple amplifier, right? So this all is the math here behind, and then I will try to evaluate what is the impedance looking into that with simple by drawing the small signal equivalent circuit, and I try to evaluate the, and then the impedance looking into this by applying some voltage, and try to evaluate the current Vx by x, that gives me the impedance, that is 1 by Gm, that is 1 by Gm is the impedance. Gm is generally large, therefore 1 by Gm is small, and therefore if I use this as a load, then if I use this as a load, then obviously since the impedance looked into this is 1 by Gm, then gain is Gm R naught minus Gm into right. Therefore, since impedance is small, then obviously gain will be small. This is through intuition we can tell without doing any math and all. Still, if you want to go with it, you can go with it. But then, but it's simple elegant circuit here. So the gain is simply minus Gm into R naught. R naught is 1 by Gm, I said. So there is a body bias effect here. By taking the body bias effect, is actually equivalent Gm is this. So gain is simply minus Gm into R naught, but I can, how do I get this is a question here. Simply I know that this is minus Gm1 by Gm2 approximately. So Gm1 is square root of 2 ID mu Cx W by L1, and this is square root of 2 ID2 mu Cx W by L2, but ID1 and ID2 are same because both of them are in series, so everything will get cancelled. Only it's a function of the ratios of the geometries of the two transistors. Therefore, the gain is just simply ratio of the geometries of the two transistors. So simple. So vary the WLs, happily you can get to the variation in the gain, but then the happiness doesn't last for long because the gain is limited, right? So this is what is such a simple circuit here. But then if you don't want body bias effect, then obviously I said in the beginning itself, over keep that PMOS transistor here connected, then there won't be any body bias effect. Therefore, but then a factor of mu n by mu p will come into picture. Well, so this is what is your a simple what call a common source amplifier with a diode connected load, and there is here the constraints here that you can just think of is that constraints are that the gain is very much limited, number one. Number two is the difference between the two transistors, what you call the geometries of the two transistors will be too large here, even for smaller gains, that mathematically you can see. And also is the overdrive voltages is a problem here, right? So there is a the overdrive, you need to have a larger overdrive voltages, right? So these are the problems which are associated with this one. Now, if you want to get rid of that, what is the solution here? The solution is only simple. Diode connected transistor को एक नमस्कार. Then remove the diode connected transistor, and then what you will do? Just try to put a ordinary current source, because that is not behaving like a current source. I want to have a larger R naught there, so I will try to put a current source. So current source in this is what? Because the gate and the drain you have connected earlier together, so now you are removing that connection, because why did you connect earlier? Telugu we call Ullu Badakam. So therefore we don't want to derive this voltage from somewhere else. So therefore we want to just easily connect this one here. Therefore this voltage will be derived from here, right? But you know that the very shortcut has got its own disadvantage. Therefore now you try to derive. There is no alternate. There is no shortcut here. You derive it from somewhere, and therefore you try to have beautiful current source, no, all right, it's okay, right? You are able to right. Then this is what is the gain and all, right? So this is the gain is you can calculate the gain and all using that. So okay. Now quickly we would like to just know one more variation here is for the common source amplifier. We when you try to give a voltage at the gate, and then you have seen that the current is a function of what? ID is equal to half mu C of W and VGS minus whole square. For small variation in the VGS, then there is a square law relationship is there. Therefore, the current variation is varying leaps and bounds. Sometimes we don't want that. Sometimes we don't. We want to have a linear relationship between the applied voltage and the resulting current. So therefore, we want to reduce the sensitivity. So what I will do is I will try to connect a resistor in the source here. Then what happens? So when I give an input voltage V in here, a portion of the input voltage is getting dropped here. The only therefore effectively available VGS is, but the same V in, is applied. I am not changing the V in. V in remains the same, but the portion of that only appears between the gate and source. The rest gets dropped across RS, and therefore what is happening is the effectively available gate to source voltage is going to be reduced, and therefore the current variation becomes less as for the V in variation. So this is called a degenerative source degenerated common source amplifier. So okay, you can just now do the analysis, and the equivalent transconductance is GM by 1 plus GMRS. Okay. So I will not go into the math here, and the corresponding this one is here. Okay. And then it is interesting to evaluate this all is mathematical evaluation. It is a GM by 1 plus GMRS. You can easily say that when RS is very large, right, then what happens? This fellow is very large as compared to this. This goes off. GM is equal to 1 by RS. So equivalent transconductance is simply inversely proportional to the resistance. Therefore linearization took place. Or if RS is very small, then what happens? This is R is very small, let us say 0, then it is simply capital GM is small gm only, right? There is no big deal over there, right? So this all is about the common source amplifier with the source degeneration, okay? And it is interesting to evaluate the output impedance of the common source amplifier with source degeneration, and then you can see that the output impedance is going to be increased, right? Output impedance is going to be increased. It is not by surprise. The reason is what is happening is dou ID, the variation in the current here, is becoming smaller, right? So because there is a negative feedback, whatever is the voltage that is dropped across the resistance, that is reducing the effective input voltage, and therefore you can see the variation in the current is small. So because variation in the current is small, impedance is more. This is simple intuition you can say. Therefore output impedance is larger. Therefore that is you can always prove it through the mathematics here, okay? Therefore this all is that math and all. And we will try to quickly move towards, we will not do all this. The cascode we have seen it enough, probably will not deal much about that. Yeah, a cascode, I just would like to mention one thing, that in the load of the cascode should always be another cascode. Otherwise what happens, the whatever you have improved the output impedance, that get lost. If you try to, the cascode I have designed already, but you try to put one useless resistance over there, whose resistance value is less than the improved resistance, it comes in parallel with this, and therefore when two resistances are in parallel, then obviously equivalent resistance is smaller than the smaller one, right? Therefore that is meaningless. Therefore try to put in the load also as a cascode, right? Then what happens is you will get a larger impedance, okay? Therefore larger output impedance, larger gain you will get. The another important property for the cascode is the shielding property. Of course we have said that the shielding property, in the sense what is happening here. So the cascode can be viewed as if there is one transistor, this lower transistor is a RS is replaced by resistance. So it's just like a source degenerated common source amplifier. Why? In the sense, when you are going to evaluate the output impedance, how do you evaluate the output impedance? When you are going to evaluate the output impedance, you are muting the input at the bottom, which is gain transistor. I am not giving in the input signal. When I am not giving in the input signal, it is just like a resistor for me. Therefore there is nothing wrong in just to replace it by a resistor, right? So therefore the bottom transistor, driving transistor is a resistor, right? Now what is it I am doing? I am evaluating the output impedance. When I am going to evaluate the output impedance, how is it I am evaluating the output impedance for any circuit? I will mute the input signal, I will try to apply voltage at the output node, and give some voltage and try to evaluate dou Vd by dou Id, that is the output impedance, right? So here also when I trying to do that for the cascode, then you are muting this fellow at the bottom transistor, the driving transistor. When you do that, it is just like a resistor. So therefore then it just mimics like. And how about the upper transistor? Upper transistor anyhow gate is a DC voltage, that why say though that is always ground only, right? So just like this is a common source amplifier with a source degeneration, and here now I am trying to apply some voltage change, and then I try to evaluate for delta V what is delta Ix, right? I want to evaluate. When I try to do that, so that can be seen as if this is delta V, right? So this delta VRS is equal to delta VRS. This is the delta V is applied here. This is total delta current. I can view because this potential is same here and here also. I can view as if delta V is here, delta V is here. So delta V here, delta V here. So therefore I can view this further as if what the impedance in looking into this is 1 by Gm plus GMB. Therefore I will replace this by a resistor with the resistance of 1 by Gm plus GMB. So this is simply 1 by Gm plus GMB and grounded, and this is R0, this is delta V, and this is delta VRS, right? Delta VRS is what is the voltage drop across the resistance RS in response to change in this is delta VRS, right? Now, so delta VRS, what is this voltage here? If there is a change here delta V, what is delta VRS we want to evaluate? Delta VRS is equal to delta V multiplied by, where is delta V? Delta V I am giving here, delta V multiplied by divided by, what is this? This is R0 plus, these two are in parallel, R0 plus RS is in parallel with 1 by Gm plus GMB, right? RS in parallel with 1 by Gm plus GMB. So all this gives me current here multiplied by 1 by Gm plus GMB in parallel with RS. That because I want this voltage, right? Did you understand or not? What I am trying to do, I am giving a delta V here. I want to evaluate what is this voltage delta VRS here. How do I do that? Delta V divided by delta. First of all, I am calculating current here. Delta V divided by R0 plus these two in parallel gives me the total current. That multiplied by these two in parallel gives me voltage here. That is what exactly I have done there, right? Delta V divided by 1 by Gm plus Gm in parallel with RS plus R0, the current multiplied by 1 by Gm plus Gm in parallel RS. So if you try to do the small evaluation, what I am getting here is, so what here by inspection itself I can say this delta VRS is now in the numerator and denominator. If you try to compare, numerator is larger or denominator is larger? Denominator is larger because denominator has got R0 plus this all is there. R0 is big, so denominator is larger. This itself clearly demonstrates that delta VRS is only a fraction of the delta V. Delta VRS is only a fraction of delta V. So if there is a change in the output node here by delta V, only a fraction of that only appears at this node, right? So it is as good as I am driving a vehicle, right? So the road I am just trying to move from Vijayawada to Challapalli, there is a village there, right? So when you try to move there, then the road here after Pamaru there is another town. Then you start all movie will be appearing in front of you. Then there is a lot of variations are there, the ups and downs on the road, and therefore your back will be spoiled. Therefore what you will do, you will prefer to have good shock absorbers for the vehicle. Then it absorbs all the bumps, right? It will not allow to reach to your back, right? Therefore exactly the same thing here. Therefore if there is some variation here that is being dropped here, only a fraction of that only appears to reach in the top here. What is this node? This node, what is this node? This node is the drain of driving transistor. That is not the drain of the driving transistor. So beautifully it is acting like a shock absorber, right? So in the cascode, therefore the cascode transistor which is sitting on the top of the driving transistor is behaving like a shock absorber or a shield. So between the output node voltage variations to the, then that is earlier what I said. Oh, if it varies, if the drain voltage of the cascode of the driving transistor, if this varies, then VGS of that varies, and therefore current is also decreasing. Therefore we were crying, right? Now that whatever is there, that is being addressed now, right? To some extent at least that variation is being arrested. This is what is. It is not that much of variation will not be there. It is acting like a shock absorber. Is it okay? Right. So this is what is shielding property of the cascode. So once this is done, very quickly I will try to just say something about the differential amplifier. Why you want to just go for differential amplifier? Differential amplifier, the purpose, differential signaling and the other one is single entrant signaling. There is a difference here. So what is the differential signaling? What is the differential signal? Anyhow, before I'm just going. Should I stop? Okay, I'll stop here.
So, good morning all. So today I am going to teach the processor design, both data path and controller design. So here the complex digital systems, so we can design data path separately and controller separately. Later we are going to integrate both data path and controller. The simple systems integrated both data path and controller, so together we are going to design. But here, okay, first we plan the data path components, then later we are going to see the controller components. So this is the top-down design approach. Okay. In top-down design approach, we just plan the specifications. Okay, what are the components are required, data path components. We'll identify the data path components. Okay, then we'll develop the data path. Then later we are going to decide and design the controllers. Data path components in digital system are mainly like multiplexers, adders, okay, encoders, decoders, even sequential like registers, counters. Okay. They all comes under data path, ALU. The controller we are going to design by using FSM, finite state machines, algorithmic state machines. Okay. So these are the sequential state machine tools we can use to develop the controller. Okay. So in this processor, the MIPS processor, MIPS is microprocessor, so without interlocked pipeline stages. So MIPS processor, with 32-bit Risc processor, the complete Risc architecture, the total as it is I am not going to design. So this is customized one. We can develop so our own instruction set, small instruction set with small controller we can develop. Okay. Just 1 second. This here, these are the instruction formats, what different types of instructions and instruction formats. So we are ready to look at an implementation of the MIPS instruction set simplified to contain only the few instructions, arithmetic and logic instructions, memory reference instructions, and control flow instructions. So these three types of instructions it is going to support. So addition, subtraction, AND operation, OR operation, and compare operation. Set less than. Okay, set less than is compare the two instructions and it is going to set if it is less. Then memory reference instructions, load word and stored word instructions, and the control instructions like the jump instruction. Okay, control flow instructions, branch unequal, that is a conditional jump instruction, and J is here jump on unconditional instruction. These are the instructions it is going to support for this MIPS architecture. If you see that instruction template or instruction format, because the processor it won't understand any the assembly code or C code directly, so it will understand because the digital circuit will follow only the digital binary bit patterns only, right? So finally these instructions, to write a program in assembly language by using these instructions, so that we have to translate into machine level language, machine code, okay, by using assembler. Each instruction category there is an instruction template, this is instruction format. The R format, I format, J format. These are the three different formats of the instructions. I format, the R format supports the arithmetic logic instructions. I format supports the memory reference instructions, and J format is for control instructions. Okay. So here if you see, this is a total, all instructions are equal size instructions, 32-bit instructions. All are equal 32-bit instructions. So in this architecture, there are the internal registers are there. Registers. So programmable registers, 32 registers are present inside the architecture. So these 32 registers we can use for temporary storage. Okay, when the program is executing, it will store the temporary data, or the results, partial results will be stored in these registers. So those registers we can use as a source operands. We can store the source operands as well as the destination operand, the partial results can be stored in these registers. So for that, so these two registers, the 5 bits address, this is the 5-bit address of that register, RT and RS, source, target, destination. Okay, so 5 bits indicate that, so we can, these 5 bits will indicate the address of the 32-bit register that are present in the architecture. So out of that 32 registers, R0 to R31, so which register we are using as a RS? That number, that 5-bit binary number we are going to enter there. Each register there is a unique address. Okay. So similarly, RT register address you have to enter here, that 5 bits, and these 5 bits will indicate that RD destination register address. Okay. Then coming to this last 6 bits, that will indicate the operational code, operation code. So what type of operation this instruction is going to perform, the operation code is indicated in last 6 bits, and these 5 bits are the functional code. This is the functionality of the instruction, and this is shift demo. How many? So because the instructions can be shifted, right shift, left shift, or rotation operations. How many bits we can shift left, or we can shift right? That will be indicated in the shift demo. Similarly, I format and J format. So I am going to discuss when we are actually going through the slides. Yeah. If you see this, the architecture is a high-level abstract view of, so how the instruction can be executed, any microprocessor, how the instruction will be executed. It will be a fetch operation, instruction fetch, then instruction decode, then operands read, right, execution, then write the results back. These are the steps you will follow for execution of any instruction. So in this, the fetch operation, fetch the instruction from memory and increment PC. What is PC? PC is a program counter. Program counter indicates the address of the next instruction to be executed. Program counter always keeps track of the program execution. It will indicate the address of the instruction to be executed. Program counter. Okay. So here use the program counter to read the instruction address, so fetch the instruction from the memory and increment PC. Use fields of the instruction to select the registers to read and execute depending on the instruction, and then repeat. This is the process it has to do for the instruction execution. So for that we require the program counter. One program counter is required, and one program memory, this is the instruction memory. There here where program is going to be stored. Then next is the registers I told. The number of registers here, 32 registers, each of 32 bit. Then followed by ALU, arithmetic logic unit. Then data memory. So here the partial results are data that we are going to be stored in this. So these are the main components are going to be used in this processor designing architecture. So single cycle instruction we are going to develop. That means, so for all instructions will be executed in one cycle, single cycle, for all arithmetic operations or logical operations, load store instructions or jump instructions. So all types of instructions will be executed in one cycle. Right? So then pipeline, execute each instruction multiple step, that will see multi-cycle data. Okay, we can also develop, there is the advantage, disadvantage of single cycle and multi-cycle. Okay, so if you go for multi-cycle, so it takes multiple clock cycles, but clock period will be less. Okay, that efficiently we can run the instructions by using multi-cycle, we can improve the throughput also. But here actually the cycle period is decided by the longest instruction that takes the time, that will decide the clock period. So two types of functional elements in the hardware: elements that operate on data called combination elements, elements that contain data called state or sequential elements. Okay, here the clock period will be decided by the longest path, critical path. So from input to output is a state element. The state element is the propagation delay in the combination logic. Okay, how much the time it takes from the state to that input, the data it is moving from the output of this flip-flop, the sequential elements, output of this flip-flop to input of this flip-flop, the delay. Okay, that is the critical path delay, the longest path delay, that will decide the clock period of the circuit. The first component is resistors. Resistors are implemented with array of flip-flops. Okay, we can design first resistors, 32 resistors. Okay, these 32 resistors, resistor means they are flip-flops only. Okay, connecting series, the connecting of the flip-flops will become the resistor. We can store that data and we can shift the data. Okay, so here resistors are implemented with array of D flip-flops. We see this is the resistor file. The register file we are going to develop. This is required. That is required in the MIPS processor. So in this register file, this contains internally how many registers? 32 registers, R0 to R31. Each of 32 bit. Each of 32 bit, 32 registers. So right. So for this register file, how many inputs are there in this? The inputs are register, read register number 1, read register number 2, and write register and write data, and these are the read data 1, read data. These are the ports of this register file. So these are the register selection inputs. Register selection inputs. One input ports: read register number 1, read register number 2, read and write register, and then write data. So these are the two ports are available. That means simultaneously we can read two registers, read ports. These are two read ports and one write port. This register file contains so two read ports and one write port. That means at a time we can read two registers and we can write into one register. So which register that is indicated by this, the selection input, that is the address of the registers. This is read register number 1, that is the 5 bits. That is the address of the register. Read register number 1 is data read 1. Okay. So which register we are going to read? That address is indicated by this register, read register number 1 and read register number 2. Because here one register we are reading. Which register you are going to read? So that address is indicated by this 5 bits. Similarly, register 2 we are going to read. So that register 2 address is indicated by this 5 bits. Okay. Next is write register, because we are writing the one register. So that write register address is indicated by this 5 bits. This is three addresses for register selections. 2 read registers and 1 write register. So that means this register file, it supports 2 read operations and 1 write operation at a time. Two registers we can read, and also at the same time we can also write to one register. Any doubts in this? Okay. Then you see this, the design is simple. Register creation is simple, very logical. You can write easily just one line only. Simple, one line. Input assigned to output assigned. At the clock is equal to 1. Or if it is edge, so clock rising integer, falling edge, the input will be assigned to output. That's all. Only one line code only. 32-bit register writing Verilog creation is simple, very simple. So that we can create like this, the 32 registers here. Okay, these 32 registers, we need 2 read ports here to create. How to create read ports? These 32 register outputs are connected to the data selector, multiplexer. Okay, 32 input multiplexer. That we call it as a data selector, because each input is a 32 bit. Understood? This maxi is 32 inputs. Okay? 32 inputs, each input is 32 bit. Okay? Each input is 32 bit. Right? So to select this one of the input, how many bits are required here? multiplexer selection inputs. How many bits are required to select the multiplexer inputs? So 32:1 mux. Okay. So this is 32:1 mux. How many selection inputs are required to select these inputs? 5 bits. Okay. This is the read register number 1. That is the 5 bits here. These 5 bits are used to select any one of these 32 registers. That is the read register address. This is nothing but a read register address that will select one of these 32 registers. Okay. Another read register. This is again second read register data. Again same 32 input, one more mux. One more mux is a second mux, second multiplexer. Again 32 bit input. Each input is 32 bit, and selection input of the second mux is again 5 bits. This is 5 bits again, so that we can select here by here one register we can select, here you can select another register. 2 registers at a time you can select by using these 2 selection inputs. 5 bits register selection address, here again second register selection address. Okay, so this is about simple. Read ports are implemented with a pair of multiplexers, 5-bit multiplexers for 32 registers. Okay, so that means 32:1 data selector, 32:1 data selector, 5 bits of the input. The next is a write port. How to create a write port? 2 read ports are created by using simple multiplexers, 2 multiplexers. Okay, then write port creation, we have to select one of the register to write. So for that, this is register number, this is 5 to 32. Okay, so this 5 to 32 decoder. So 4 to 16 decoder, 3 to 8 decoder, Similarly, 5 to 32 decoder. We have to use 5 to 32 decoder. 5 inputs, 32 outputs. Okay, so based on this 5 bits input, so one of the output is going to be 1. Decoder output, one of the decoder output is going to be 1. So that one output is connected through AND gate. There are AND gate inputs. AND gate. So then write signal, the write data. Okay. So this is a write data. This is a register selection. Then this is a write signal. One control signal, write signal. This is only one bit. Write signal. If this bit is 1 and this decoder output is 1, that particular register is going to be selected. Out of these, how many registers here? 32 registers. One register only we have to select. We have to select one register to write. So that which register, how do we select this? That based on this number. This number is 5-bit number. This is a 5-bit number. So this will select this decoder output. One of the decoder output is going to be set to 1. Okay. Let us say suppose if we give 0, 0, 0, 1. So which decoder output will be 1? This 1 will be 1. This 1 is going to be 1, logic 1. If this is logic 1, okay, then it's a write signal. When you are writing the data, this write is going to be also 1. Inverted, actually write is low signal, but with inversion you can make it 1. Okay, so this 1, 1, so then AND gate output is 1, then this register will be selected. Or clock, so register is going to be selected. Okay, so once this register is selected, then whatever the data that you are going to write, this data, that will be returned to that register, the D input. D input is the 32 bit. This D input is 32 bit. 32 bit data we are going to write. Is it clear? So 2 read ports and 1 write port we can create simply by using 2 multiplexers and 1 decoder and some gating logic, by using gating logic. Okay, now you see now. So this is a register file, 2 read ports. 2 registers we can read. So by using this address, read register number 1 5 bits, read register number 2 5 bits, and write register. So write register address is this and data is that one. So this is a write data. So 2 read ports and 1 write port are created into a register file of 32 registers, each are 32 bits. The simple Verilog code only you can write simple. These all components I have discussed and shall discuss. Then we fabricate using Verilog. Verilog simple code. Verilog code, Verilog, right? You can create Verilog this register file. You can create these multiplexers and you can connect like this simple. And here also simple decoder. Verilog code you can write. and gating log on gate and connect to this register. Register creation is simple, I told already, just only one line only. Input as a D will be assigned to Q when clock is equal to 1. That's all. That is the register. The D is the 32-bit you have to define array, and Q also you have to define 32-bit. So our first implementation of which will use a single long clock cycle for every instruction. Every instruction begins on one up clock or one up or down the clock edge and ends on the next up or down the clock edge. So one clock cycle. So because we are going to use either rising edge or falling edge or up or level triggered clock high or clock low you have to use. Okay. Yeah. You see next is here fetch operation. So that instruction store fetch for PC increment. Okay, what are the components in this instruction memory? Instruction memory, it will store the programming instructions. Memory also you can create easily in Verilog, simple Verilog code you can write and it will create this memory, instruction memory. So two-dimensional memory array creation is the memory creation. Okay, so then followed by the program counter. Program counter is what? Program counter is here. It is a counter. It will be counter. Counter can be count the events or pulses. It will increment by 1, increment by 4, or increment to whatever way you desire. Okay. Here we are developing the counter. There is one register and one adder. Register and adder. The program counter is implementing through register and adder here. The program counter and one adder is there. You see here, this is the program counter data path. This is the instruction memory. Program counter always indicate the address of the instruction memory. So, okay. So it will indicate the address of the instruction to be executed. So that's why this program counter output is connected to address input of the instruction memory. This program counter. So because here one adder is here, using one adder. The program counter current value, current address. So for example, initially 0. Program counter address is 000. So that 0 is connected here. Then 4. This is a fixed value always. 4. So 0 plus 4. That the 4. That 4 will be loaded to this PC. So that means program counter always indicate address of the next instruction. Suppose if it is executing the program current instruction at the 0 address. So program counter will indicate the next instruction address. Next instruction address is incremented by 4. Why it is incremented by 4? Why not 1? Huh? Why? Because here each instruction is 32-bit instruction. Each instruction is 32-bit instruction. Fixed size. Okay? So each instruction will be stored in 4 memory locations. Because each memory location, instruction memory location, it will store only 8 bits. Okay? To store one instruction, it requires 4 locations. 0, 1, 2, 3. It will be loaded one instruction. 4, 5, 6, 7, second instruction. So like that, every 4 locations one instruction will be stored there. Because each instruction is 32-bit instruction. So currently it is executing current instruction at the 0th address. The next instruction address is at 4. Because it will increment by 4. So that's why this 4 is there here. 4. It's a constant value. Every time it is going to be incremented by 4. Okay, this way the program counter can be designed simply. One adder is required. What is the size of this adder? What is the size of this adder? 8 bit, 16 bit or 32 bit or 4 bit? Huh? What is the other input? What is the size of this input? This input, how many bits? Huh? What is the size of this address?
32 bit.
Huh?
32 bit.
What is address? Address size? Address already I told, this is always, this registers all, everything is 32 bit. 32 bit address bus, 32 bit data bus. That internal architecture is 32 bit. Okay? So this address is 32 bit. The program counter is also 32 bit. Okay? So it will indicate the 32 bit address. So this input is 32 bits. And here the constant 4 in 32 bit format only. constant 4 in 32-bit format. Then this adder is 32-bit adder. This is 32-bit adder. Okay. So 32-bit adder is required. That adder it will update the address of the instruction every time by 4 and it will be stored into the program counter. Program counter is 32-bit. All internal registers, whatever I discussed, all are 32-bit registers. Okay. Yeah, if you see this, you can also verify this. The instruction PC is equal to PC plus 4. PC is program counter. Every time it is going to be incremented by 4. So first, the PC is indicating current instruction. PC will be automatically incremented by 4 to indicate the address of the next instruction. So here, by adding this 4, that will be incremented by next instruction address. We just see the first PC value will indicate the address of the memory. Okay. PC is indicating current instruction address. Okay, 0th location address. Then later PC will be updated by next instruction address. Okay. So it will take the current address and will add that 4 and then updated value will be stored in the PC again. PC is equal to PC plus 4 is implemented. So in this fashion, program counter incrementing the operation. So here we are not designed a counter. What is PC here? PC is not a counter here. PC is only register over here. Just holding, writing the data. Just writing the data into this. Okay? PC here we are implemented as a register. PC plus this added together, it becomes a counter. Okay? This 32-bit register plus this added together, it will act like a counter, program counter. PC plus incrementer. Okay, right? Understood this? So this address it is going to read instruction, reading the fetch operation. This is fetch operation, reading instruction from the instruction memory. Fine. So instruction we are reading from the memory location, indicate the address indicated by the PC. Next is R type of instructions, how do you implement, what are the components are required to implement the R type of instruction. What are the R type of instructions? What are the R type of instructions? So here R format instructions. These are the R format instructions. You see addition, subtraction, AND operation, R operation, and set less than the compare instruction. These are the instructions are R format instructions. Okay. So now to implement the data path, first we are going to design the data path to implement these instructions. AND operation, R operation. Okay. Addition, subtraction, AND operation, R operation, compare operation. So the data path we have to design. First we have developed register file we have created. Then later program counter logic also we designed. The next is the R format instructions data path we are going to see. So here R format data path. So here register file is required because R format instructions it won't require any memory references. Memory it is not going to read or write from the memory. The instruction execution. Okay. So register file, then ALU, then followed by one ALU, because here ALU is going to do addition operation, subtraction operation, AND operation, R operation, compare operation will be done in this ALU only. Okay. So this ALU internally we have to write that add operation logic. Okay. Add operation logic, subtraction operation logic, and all Boolean operation, AND operation, R operation, compare operation, all the logic will be we have to write in this ALU. Okay. So then by interconnecting this register file to that ALU, so we can able to run all R format instructions or R type of instructions. So right, we see the register is connected to read ports because for any instruction, add instruction, we require the 3 operands. Okay. So we require 3 operands. So For example, add R0, R1, then comma R2. So this we call it as a mnemonic instruction. It's a mnemonic. Okay. Then this one is your operands. We call it the operands. 3 operand instruction. So these are the 2 operands. These are the source operands. These 2 are source operands. Source operand, and this one is your destination operand. Destination operand. Okay. So how it is going to work here? R1 plus R2. The result is stored in R0. So that's why these 2 are source operands. Operand R1 content and R2 content is added, and the result is stored in R0. 3 operands are required. So to execute this add instruction, how many registers we are required? 3 registers. That means 2 registers we have to read. We have to read 2 registers. This is a destination register. That is going to be write. We have to read 2 registers and write 1 register. Okay? So that's why you can see here, these are the 2 registers we are going to read. So that means here R0, R1. R0, R1 registers we are going to read from these 2 read ports. Okay? Then after that is going to be add. After addition, the result is we are going to write again. The result is writing into R0. So right? So then write port. So that means 2 read ports and 1 write port is required by the register type. So at a time we can read and compute the result. After computing the result, then we are going to write into the write register. All these operations, to read operations, then computation operation and writing operation. So all these will be completed in 1 clock cycle. Okay? So then this instruction. So if you see here, the instruction is 32-bit instruction is required. So this instruction will indicate the address of the 3 registers. These 3 registers address is indicated in the instruction template itself. Because here we need to select 2 registers for reading, 1 register for writing. But out of that, how many registers in this? Total number of registers, how many are there?
3.
Total number of registers in the register file.
32.
Total number of registers in the register file, how many are there? Not following it all. How many registers we have created first initially? Register file creation. So here we created a register file. Here how many registers? Total number of registers? 32 registers are there, R0 to R31. So this processor internally contains 32 registers, R0 to R31. So all these 32 registers we can use as a source registers as well as destination registers. We have to select one of the registers from the group. Okay? So right. So here 2 registers we have to select out of the 32. So which 2 registers? Here R1 and R2. Let's see. Right here we have to select R1 and here we have to select R2. R1 and R2 registers we have to select. And writing one more register R0. So 3rd registers. Okay. So here we need to select these 2 registers for reading out of 32 registers and 1 register we have to select for writing. So that means these 3 registers addresses, these 3 register addresses are present in the instruction template. The instruction template indicates the address of these 2 read registers and the write register. Okay? We see that instruction template. I will show once again. So here you see this is the R format instruction template format. So in this, this RS, this 5 bits will indicate one of the registers, read register 1, and this these 5 bits will indicate. So next, one of the registers of read to register, and this one is, these 5 bits will indicate the write register address. So total, so 15 bits of this instruction, 15 bits of this is instruction, the 32-bit instruction. Okay, machine code. In that machine code, this is 32-bit. In that, the 15 bits are address of the registers only. Okay, 2 read register addresses, 1 write register address. This is indicated here. Is 15 bits. So if you see, so these 15 bits are, it will take from this instruction template from template, and it will select 2 read registers. Then the 2 read register content is going to be added. Then result is again write to one of the write register. Okay, if you see the example, you can understand. So see this is the 2 read registers RS and RT, 5 bit each. And this one is destination write register address. This is the instruction, R format instruction template. From the instruction only, so it is going to take the address, instruction template. Then it will compute that, so add RS, RT, add the RS plus RT. This RS plus RT and result is stored in RT. Okay, you see, so that is the address of the 3 registers. Is it clear or not? If you not follow, please, any questions or maybe any doubts, please stop. Okay, so it is taking the address of the registers first, then selecting 3 registers. Out of the 3 registers, 2 are for read, 1 is for write. But out of total number of 32 registers, out of 32, 3 registers we are selecting. Okay. Next is the reading the 2 registers. 2 registers, the example here, R1 and R2. So then, after that is going to add. After addition, the result is going to be, sorry. So next is, the result is going to be returned to the write register. The write register address is again, we are indicated by this RD. Write register address is indicated by RD. Read register addresses are indicated by RS and RD. 5 bits each. Is it clear? Why 5 bits each? Why 5 bits are required to select the registers? Why 5 bits are required to select these registers? This address, why address is 5 bits? No. Why do we need 5 bits to select these registers? No? Because here number of registers are 32. Out of 32, we have to select 1. That means, so 2 power 5. 2 power 5 is 32. Okay? So next is it clear? R format data path. This is the R format data path symbol on register file and ALU is sufficient. R format to execute all R format instructions. All 3 operand instructions only. Okay? The addition operation, instruction operation, AND operation, OR operation, compare operation. So all these instructions will be executed by using one register file and ALU. It can be done easily. So next is coming to data path for load store instructions. Load store means here memory reference instructions. So reading data from memory and writing to memory. Okay. So this load instruction is for reading data from memory to register. Okay. And store instruction is for writing data from register to memory. Load and store. These are the 2 instructions. And what is the data path is required to implement these load store instructions? See, so the data path here. So because the data we are going to read and write from the memory, data memory. So that's why one data memory is required. Earlier is instruction memory, the program is stored in instruction memory, and data is going to be stored in the data memory. So the data memory component is required. We are going to add data memory component and the register file, ALU and data memory. So this is the data memory unit. So the data memory creation is the memory address, the read data or write data. 2 read ports and 1 write port. Memory, how to write the memory? Memory, how to represent the memory? Okay. 1K memory. Okay, 1K memory means here 1 kilobyte. 1 kilobyte. So that means number of locations are 1K locations. So 1K memory locations. To address these 1K locations, so each location size is 8 bits. You can store 8 bits of data, right? So we require the address to address these 1K memory locations 0, 1, 2, 1, 0, 2, 3, 1K, 1, 0, 2, 4 locations. To address these locations, how many address bits are required? 10. So 1K 2 power n is equal to 10. Let's see 1, 0, 2, 4. Right? 1, 0, 1K. Okay? N is equal to 10. 2, 4, 10. So okay, here 10 address bits. This is the address input. Okay, this is the address bus A0 to A9 address. This will select one of the locations, address bus. Okay, then data, because this is the RAM type, SRAM read-write operation. RAM type of memory, read-write operation. So we require one data because each memory location is 8 bits. So we can read and write at a time 8 bits. 8 bits. Read and write. This is data bus. This is data. Okay. D0 is some data. So because here, so we can read and write through read signal and maybe and also write signal or otherwise. So separate read signal or write signal we use or otherwise. The read is the signal is 1 when the reading or 0 is 1 for write operation. Separate read and write. This way we can say the memory implementations. The number of inputs and output pins are decreased. Okay. So address inputs, control inputs, and data. Data was for read and write. So here you see this is the memory, data memory. So address, this is the address input. Then read data, then write data. Separately is indicated read data, write data. Then write memory signal and read memory signal. So okay, like here read signal, write signal, address, read write data, reading and writing, bidirectional or unidirectional. Okay. Right. So if you see here, again, here to load instruction is reading data from memory. Reading data from memory, and write instruction is load instruction is reading data from memory. Store instruction is writing data from register to memory. So if you see how many read ports are required here, because here this data path is two operations. One is read, okay, then read data from the memory, and writing into register, or write data to memory. Load instruction is reading data. This is the memory. This is the memory component. Reading data from memory and writing to the register. That's the load instruction. Okay. Store instruction is register value. Register value is writing into memory. That is the store instruction. Read data and write into memory. These are the components. Okay. The read connection and the write connection. And the address, because you see the template once again, it will be there in the next slide. If you see this is the template for the instruction for the high format instructions. High format is related to memory reference instructions. Read operation, write operation. So in this case, load word, load RT, offset RS. Two instructions, load and store. So load word, load word, or load RT, offset RS. So that means here we are reading data from the memory. Reading data from the memory. Okay? The memory address indicated in RS register. RS register indicating the address of the memory. So right? So this is nothing but this RS register, it is a indicating the address of the memory location of the data memory. Okay? And that data and plus if any offset, this is the offset. Offset means displacement address. Example I give for example you can understand also. Okay, LW RT. Then offset is let us say some 100. Then RS. From RS. Okay. So RS will indicate some address. Okay. Some address let us say 0x200. This is initially the address of the memory. Okay. This is the address of the memory. RS contains this address. RS will indicate the address of the data memory. Plus this is the offset. Offset address is the displacement. So then this displacement will be added to this. Okay. Added to this. Then we get 0x200 010. This is the address. That is the final address of the data. So this is displacement plus base. This is the base address. Base address plus displacement. This option is displacement. Any 16-bit, 8-bit number it will give the displacement address. Displacement address plus base address. That is the effective address. This is the effective address. This is the final address. So from this address there will be data, and that data is going to copy to and stored into that RT register. Okay, RT is the destination, RS is the source here, but this source register will indicate the address of the data, base address of the data. So offset slash immediate. So offset slash immediate is there. This is in the template. Just go back again. See, this is a 16-bit. 16-bit. 16-bit offset. Offset address is 16-bit. Out of 32-bit, this is the total size of instruction is 32-bit. In the 32-bit, high format instruction 16 lower 16 bits will indicate offset address. The remaining, so these two fields will indicate source register address, source register address, base register address, and target register address. Only two registers here. Base register address. This register will indicate base address of the data memory, and this register will indicate the address of the target address. Target register address. That means write register address. It's a write register address. The memory base address indicates register. And this is the instruction output. So right now if you see this RS is connected here, it will select one register will be selected because of this RS plus offset. Offset is where is the offset? This is the offset. 16-bit offset. 16-bit offset is going to here one logic is a small logic. This logic what it will do? The 16-bit offset is extended to 32-bit. This is sign extension. Simply converting 16-bit offset address into 32-bit. So sign extension will be done. Sign extension means the MSB bit of this 16-bit offset will be copied to remaining 16 bits. So that sign extension with that it will become 32-bit. Okay. Now this offset is 32-bit. Okay, because we have to add here, we are adding base address is 32-bit. And offset address is not 32-bit. Offset address is 16-bit. How to add? Both should be 32-bit, then only we can add. The adder, both these two operand, add the operand and these two operands should be 32-bit, then only we can add properly. So that's why this is is extended to W. How the extension is? The sign of this, sign may be 0 or maybe 21. Negative number is 1, positive number is 0. So that will be extended to remaining bits. Sign extension. Then later it will become W. This is W. And this is the base address. This 2000, so what I am reading this address, that is the base address. So that address I am going to read from the register, RS register. But RS register address is indicated by this RS field. RS field of the instruction template will indicate the base address. The RS field of the instruction template will indicate the base register address. That is only base register address, RS. Okay, then that content of the register, that will be, and this offset that will be, these two will be added. Okay, and this gives the effective address. Effective address here, adding this. After adding this is the final address. Offset plus base. So that address is going to memory. This will select the memory location. One memory location will be selected. Based on this address, memory will be selected. That memory location content, I am going to read to read port. This read data, read port. Okay, read port of the data memory and reading and writing to a register. So which register we have? Some register R0, R1, out of 32 register, one register. So which register I have to write? That is selected to RT. So here RT is an instruction RT. That is RT field, target register. Right? This address will select one of the registers in this. So in that register I am going to write. Okay? Is it clear? Any doubts here? So simple. See, RS and RT. Okay, two registers. One is for base address, other one is target register address. Then that is immediate address, immediate field, that is offset address. That is sign extended and control it made to control it. And then this RS register will be read. RS register, and this will be added. This is the address of the memory. Address of the memory. Then memory location content I am going to read and again write to one of the registers here. The register is, which register is going to write? What is the address of the register? Which register will be written? Register address is indicated by RT field. RT field will indicate the register to be written. This RT field 5 bits will indicate the register to be written. Okay. So here we are not using 3 register fields. Here only the I format instructions are only 2 register field instructions.